Hey everyone, and welcome to another deep dive. Today we're going to be tackling some pretty fundamental stuff. Physics and chemistry.
Yeah, two real cornerstones of, well, pretty much everything.
Exactly. And to help us navigate this, pretty massive landscape, our listener has sent us their Intro to Physics and Chemistry study guide.
hmm
It's great. We're going to pull out some of the most important ideas and
Yeah, really trying to connect them to, things everyone experiences in the world around them.
perfect.
Yeah.
So to kick things off, we got to start with the fundamental process in science, the scientific method.
Right, the scientific method, it's not just about, labs and experiments.
No, not at all.
It's really a way of thinking. It's asking questions and figuring out how to, test those questions.
Yeah, like a detective almost.
You observe something interesting. Let's say your phone battery, it dies way faster when it's cold out. And you're like, why is that?
So then you start thinking of different explanations, like maybe the cold slows down the chemical reactions in the battery or something.
Right.
Exactly. And that's your hypothesis,
Yeah.
a possible explanation. And then you got to design an experiment to test it.
And this is where it gets tricky, right? Because you have to control all these different variables to make sure.
Absolutely.
Yeah.
You only want to change one thing at a time. So in this case, you test the battery at different temperatures, but everything else has to stay the same. That way, any changes are really because of the temperature, not something else.
Makes sense. And of course, any good scientist does the experiment multiple times, just to be sure.
Yeah. Got to be sure your results are legit.
Definitely. Now, speaking of experiments, you gotta have something to experiment on, right? So let's talk about matter. Literally everything around us is matter.
From the air we breathe to the devices we're using to record this to...
Right. And this matter can exist in different states. We've got solids, liquids, gases. But wait, wasn't there a fourth one? Plasma.
You're right. There's plasma, too. Superheated matter, like you find in stars.
Yeah.
Pretty wild. But for this deep dive, we'll stick to the basics: solids, liquids, and gases. The ones we encounter most often.
Sounds good. Now, how do we even measure and describe this matter? Like, there are all these units, right? Meters and grams and...
Yeah. We use what are called SI units. It's like a universal language for science, so everyone's using the same measurements, whether they're in Europe or Asia or anywhere.
Right, so no one's getting their kilograms mixed up with their pounds or anything.
Exactly. No confusion. Keeps everything clear.
Mhm.
The meter for length, the kilogram for mass, second for time, the essentials.
Okay, so that's how we measure this stuff, the matter. But what about how it movies? That's where physics really kicks in, right?
Absolutely. And we start with motion, how things change position over time. Now, two ideas that often get confused are speed and velocity. They sound similar, but,
Yeah, I remember having trouble with those.
well, think about driving a car. Say you're going constant 60 miles per hour around a circular track. Your speed is the same, right? But your velocity is constantly changing.
Because you're changing direction.
Yep. Velocity takes direction into account, while speed doesn't.
Got it. So velocity is like speed, but with like a built-in GPS or something.
Exactly. It knows where you're headed. Now let's add another layer: acceleration.
Okay, acceleration. That's how quickly your velocity changes, right?
Yeah.
Whether it's speeding up, slowing down, or like you said, changing direction.
You got it. Stepping on the gas in your car: acceleration. Hitting the brakes.
Yeah.
Deceleration or negative acceleration.
And then there's that cool concept of terminal velocity.
Oh yeah, when something's falling through the air, like say a skydiver.
Don't they reach a point where they can't fall any faster?
Exactly. Air resistance balances out gravity and they hit their top speed, terminal velocity.
Makes sense. Now, speaking of falling objects and stuff, there's that other concept I always struggled with, momentum.
Yeah, momentum. It's basically how much oomph something has when it's moving, a measure of its mass and velocity.
So like a bowling ball rolling down a lane, the heavier it is, the faster it's going, the more pins it's likely to knock down.
Exactly. More momentum. Now, where things really got tricky for me were collisions.
Oh yeah, collisions. Elastic collisions and inelastic collisions?
Yeah, those always trip me up. Okay, imagine two billiard balls colliding. In an elastic collision, they bounce off each other perfectly. No energy is lost.
Like a perfect clink sound.
Right, but in an inelastic collision, some energy gets lost, maybe as heat or sound. The balls might stick together a bit or dent.
So elastic collisions are like bouncy balls, and inelastic collisions are more like dropping a lump of clay.
Perfect analogy. Now, get ready, because we're about to dive into the big leagues. Newton's laws of motion.
Oh yeah, Newton's laws, those are like the bedrock of physics, right?
They really are. They explain how objects move and interact,
I
and
remember them being a bit intimidating.
let's demystify them. So Newton's first law, the law of inertia. It basically says that an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by a force.
So, like, objects are kind of lazy. They like to keep doing what they're already doing unless something makes them change.
Exactly. Think of a book sitting on a table. It's not going to suddenly fly off unless someone pushes it or something, acts on it.
Makes sense. Now, what about Newton's second law? That one always seemed more complex.
Well, it describes how force, mass, and acceleration all relate. It's often written as F is ma, where F is force, m is mass, and a is acceleration.
So if you push a shopping cart with more force, it'll accelerate faster. But if the cart is heavier, full of groceries, it's harder to get it moving.
Precisely. More force, more acceleration. More mass, less acceleration for the same force.
Okay, that's starting to click. Now, for the grand finale, Newton's third law. This one always seemed a bit counterintuitive.
It does seem kind of strange at first. It says that for every action, there's an equal and opposite reaction.
Meaning?
Forces always come in pairs. If you push against a wall, the wall is pushing back on you with the same amount of force.
Whoa, so it's like a physics dance-off. Every push or pull has a partner doing the opposite move.
Yeah, great way to put it. And this applies to everything from like rockets launching into space to just walking across a room.
Wow. Okay, so Newton's laws are really everywhere. And this all connects to another big idea, the conservation of energy.
Ah, yes. Energy can't be created or destroyed, only transformed from one form to another.
So it's like a cosmic recycling program for energy. It can change, but the total amount stays the same.
Exactly. Imagine a roller coaster going up a hill. It's building up potential energy because of its height. Then as it goes down, that potential energy is converted to kinetic energy, the energy of motion. The total energy remains constant.
Great visual. So we've talked about energy. Let's dive into a concept that affects us everyday work. In physics, work has a very specific meaning, right?
Yeah, it's not just about, going to the office.
Hmm.
In physics, work happens when you apply a force over a distance. So lifting a weight, pushing a box across the floor, that all takes work.
So even those everyday chores like carrying groceries or climbing stairs involve work. And I'm guessing this ties back into those ideas of kinetic and potential energy we were talking about.
You bet. It's like that roller coaster analogy we were just talking about. When it's at the top of the hill, it has a ton of potential energy stored up because of its height. Then, as it plummets down, that potential energy is converted to kinetic energy, the energy of motion.
Exactly. And then there's power, right, which is all about how quickly you can do work.
Exactly. Like a super powerful car can accelerate super fast because it can generate a lot of work in a very short amount of time.
So basically, a souped-up sports car has way more power than, say, my old minivan.
You got it. Now, shifting gears a bit, let's talk about heat and temperature. I always found those two a little confusing.
Yeah, me too. They seem related, but not quite the same thing.
Right. Temperature, it's a measure of how much the particles inside something are like jiggling around.
Mm-hmm.
The more they jiggle, the higher the temperature. Heat, on the other hand, well, that's the energy that's transferred between objects at different temperatures.
Okay, so like when I touch a hot stove, ouch,
Mm-hmm.
heat is flowing from the stove to my hand, and that's what causes the temperature of my skin to go up.
Exactly. And we use different scales to measure temperature: Celsius, Fahrenheit, Kelvin. Celsius is the one most people use worldwide. But in science, we often use Kelvin, which starts at absolute zero.
Absolute zero. That sounds intense.
Yeah, it's the coldest possible temperature. Theoretically, all molecular motion stops at absolute zero.
Brr, that's co-LD. Okay, let's switch gears again. Electricity and magnetism. I remember being fascinated by magnets as a kid, but never really understanding how they worked.
Yeah, magnets are pretty cool. It all comes down to the movement of electric charges. Every atom has electrons whizzing around its nucleus, and those moving electrons, well, they create these tiny magnetic fields.
So it's like every atom is a mini magnet.
Kinda. But in most materials, these mini magnetic fields are all jumbled up, pointing in random directions, so they basically cancel each other out.
Ah, so they're all working against each other.
Exactly. But in magnets, something special happens. All the magnetic fields line up in the same direction. And that's what creates a net magnetic field, what we feel as magnetism.
So a magnet is like a super organized army of electrons, all their magnetic fields pointing the same way.
Yeah, great way to picture it. And of course, opposites attract. north and south poles.
Yeah. And this whole magnetism thing has led to so many awesome inventions, compasses, MRI machines.
For sure. Now let's talk about electricity. It's closely related to magnetism.
Okay, bring on the electricity. How does it connect?
Well, electricity is all about the flow of electric charges. Think of it like water flowing through a pipe. The charges can be electrons, like in a wire, or ions, like in a solution.
Got it. So voltage is like the water pressure that pushes the charges along, right? And current is the amount of charge flowing per second.
Exactly. Voltage is the push, and current is the flow. Now, remember resistance. It's like the width of the pipe. A narrower pipe makes it harder for water to flow, and a material with higher resistance makes it harder for electric current to flow.
Ah, so resistance is like the electrical friction.
Good analogy. Now, this brings us to circuits, the paths that electricity flows through. There are two main types: series circuits and parallel circuits.
I remember those from school. Series circuits are like one long line, right? And if one part breaks, the whole thing stops working.
Yeah, like those old Christmas lights. One bulb goes out, the whole string goes dark.
Ugh, those were so frustrating. So parallel circuits are different.
In a parallel circuit, the components are connected on different branches. So if
Mhm.
one part fails, the other branches can still keep going.
Ah, so that's why if one light bulb in my house burns out, the rest stay on.
Exactly. It's way more practical for, well, pretty much everything.
Makes sense. And to measure how much electricity we use, we look at kilowatt hours, right? That's what's on my electric bill.
You got it. A kilowatt hour is a measure of how much power is used over time. Basically, how much work your electrical appliances are doing.
So my power-hungry fridge is racking up those kilowatt hours. All right, let's ride the wave and talk about, well, waves. Sound waves, light waves, it's all pretty amazing.
Waves are just disturbances that carry energy, but they don't actually move matter, like a ripple on a pond. The water molecules don't actually travel across the pond, just the energy of the wave does.
So waves are like energy surfers. They ride along, but the stuff they're riding on basically stays put.
Yeah, great way to think about it. Now, there are two main types of waves: transverse waves, like the ripples on a pond, and longitudinal waves, like sound waves.
So in a transverse wave, the particles move up and down, perpendicular to the direction the wave is traveling. But in a longitudinal wave, they move back and forth, parallel to the direction the wave is traveling.
Exactly, like a slinky. Now, waves have these important properties: wavelength, frequency, and amplitude. Wavelength is the distance between two crests, or peaks, of a wave. Frequency is how many waves pass by a certain point in a given time. And amplitude, that's the height of a wave, which tells us about its intensity.
So a wave with a shorter wavelength and a higher frequency would sound higher pitched.
Precisely. Think of a high-pitched whistle versus a deep rumble. And the louder the sound, the greater the amplitude of those sound waves.
And what about echoes? That's when sound waves are reflected, right?
Exactly. When sound waves hit a surface and bounce back, that's reflection. And if those reflected waves reach our ears, we hear an echo.
And then there's diffraction, how waves can bend around corners, like when I can hear music coming from another room, even if the door's closed.
Right. Diffraction is all about how waves bend as they pass through openings or around obstacles.
Yeah.
That's why we can hear sounds even when we're not directly in line with the source.
Ah, so that's how I can eavesdrop on conversations. Just kidding. Now, what about refraction? That's when waves bend as they pass from one medium to another, right?
Yeah, like when a straw looks bent in a glass of water.
Exactly.
That happens because the light waves slow down when they move from air into water, and that change in speed causes them to bend. And last but not least, we've got to talk about interference, how waves can interact with each other. Constructive interference amplifies waves, making them stronger, and destructive interference, well, it cancels them out.
So like noise-canceling headphones, those use destructive interference to block out all the unwanted noise, right?
Exactly. They create sound waves that are perfectly out of sync with the noise, so they cancel each other out. It's like using sound to fight sound. Pretty ingenious.
That's amazing. Okay,
Yeah.
let's shift our focus now and shine a light on, well, light,
Yeah.
and in the fascinating world of optics.
Light, it's a form of electromagnetic radiation, and it travels super fast. Something like 299,792,458 meters per second.
Wow, that's almost 300 million meters per second.
Wow.
Talk about a speed demon. And I remember learning that light can act like both a wave and a particle, which always blew my mind.
Yeah, it's one of those mind-bending concepts in physics, wave-particle duality. Light can exhibit properties of both waves and particles. Now remember, the electromagnetic spectrum, it's the entire range of electromagnetic radiation, from radio waves to gamma rays.
Yeah, it's like a cosmic rainbow of energy. And visible light, the stuff we can see, is just a tiny sliver of that entire spectrum.
Exactly. Each color we see corresponds to a different wavelength of visible light. Red has the longest wavelength, and violet has the shortest.
RYGBAV, red, orange, yellow, green, blue, indigo, violet, the colors of the rainbow. It's incredible how our brains translate these different wavelengths into all those amazing colors we see.
It really is. Now let's talk about how we can manipulate light using mirrors and lenses. Mirrors, they reflect light, while lenses refract or bend light.
So a flat mirror like the one in my bathroom creates a virtual image that looks like it's behind the mirror, flipped left to right.
Exactly. And curved mirrors, they can do some pretty trippy stuff to images. Think about those funhouse mirrors that make you look all stretched out or squished.
Yeah, those are hilarious. How do those work?
They use concave and convex mirrors to create those distorted effects. A concave mirror curves inward like a bowl, and it can magnify images. Think of a magnifying glass, focusing sunlight. A convex mirror curves outward like a dome, and it gives you a wider field of view.
Got it. And lenses are used in all sorts of things: glasses, telescopes, microscopes. They work by bending light rays to either focus them or spread them out.
Exactly. A convex lens, thicker in the middle, focuses light rays, making objects appear larger. A concave lens, thinner in the middle, spreads light rays out, making objects appear smaller.
It's amazing how we can use these simple optical tools to do so much with light. From correcting vision to exploring the far reaches of space, optics has revolutionized our understanding of the world.
Yeah, it really has. And it all goes back to those basic principles of light and how it interacts with matter.
I mean, it's kind of mind-blowing when you think about it. All of this physics and chemistry stuff, it's not just like theoretical, it's the foundation for so much of our technology.
Yeah, absolutely. Everything from like smartphones to medical imaging, it all comes down to understanding these basic laws of nature and then
Yeah.
figure out how to use them to our advantage.
Right. We've covered a ton of ground in this deep dive, from the tiniest particles of matter to the forces that shape entire galaxies. It's a lot to take in.
Well, for sure. But hey, you've officially leveled up your science knowledge.
Woot woot! Level up. But this
Yeah.
is really just the beginning, right? There's always more to discover, more questions to ask.
Absolutely. Science is all about that constant exploration, the never-ending search for answers.
And that's what makes it so exciting. It's like a journey with no final destination, just a constant unfolding of knowledge.
Exactly. And the coolest thing is that the most exciting discoveries are often the ones we haven't even imagined yet.
So true. So everyone listening out there, keep that curiosity burning. Keep asking those questions, keep learning.
Yeah, who knows? Maybe someday you'll be the one making those groundbreaking discoveries, pushing the boundaries of human knowledge.
That's the awesome thing about science. It's not just about individual brilliance. It's a collaborative effort, a shared pursuit of understanding.
And by sharing what we know and inspiring others to be curious, well, that's how we make progress. That's how we pave the way for future generations to unlock even more secrets of the universe.
Couldn't have said it better myself. This has been an amazing journey through the worlds of physics and chemistry. A huge thank you to you for joining us on this deep dive, and of course to our listener for sending in their study guide.
Yeah, it's been a blast. Always love talking about this stuff.
So to everyone out there, keep exploring, keep those questions coming, and most importantly, keep that spark of scientific curiosity alive. Until next time.